and I'll start introducing you. So, so Hui Cao is the John C. Malone Professor of Applied Physics and a Professor of Electrical Engineering at Yale University. She received her PhD degree in Applied Physics from Stanford University in 1997. Prior to joining the Yale faculty in 2008, she was on the faculty of Northwestern University from 1997 to 2007. Her technical interests and activities are in the areas of mesoscopic physics, complex photonic materials and devices, nanophotonics, and biophotonics. She authored or co-authored 1 monograph, 12 book chapters, 7 review articles, and 260 journal papers. She is a fellow of the APS, OSA, AAAS, and IEEE. And today she will speak to us about mesoscopic optics. So it's our great pleasure to have you here, and whenever you're ready, start.
Okay, yes, so I'm ready now. Okay, first let me thank Judy for this invitation. It's really my pleasure to give this talk about our work. I would hope to come to visit. Actually, I visited Arizona, I think, I forgot, like 5 years ago, or maybe 7 years ago. It was really a great experience. So hopefully I'll be able to have a chance chatting with you after this talk. And if you have any question during my talk, please feel free to interrupt me at any time. And I'll be happy to answer any questions you have. So the topic I'm going to talk today is mesoscopic optics. So let me first introduce what is mesoscopic optics. To start that, let me first introducing what is a mesoscopic physics. So mesoscopic physics, it is a very recent branch of condensed matter physics. It's really studying the the transport of of electrons, on the mesoscopic scale, which means between macroscopic scale and a microscopic scale. For example, there's a small nanowire or in a quantum dot. And because the size of the system is smaller than the dephasing length or decoherence length of the electron at a low temperature, then the interference of coherent electron wave becomes important. And that actually can lead to very famous phenomenon. I think you may have heard already, Anderson localization or universal conductance fluctuation. And because all these phenomena result from the wave nature of electron, so this actually also exists for other type of waves, like the classical waves. For example, for light, for microwave, for acoustic wave. And if we consider for light, because the coherence length for light is much longer than for the electron, so we can really do all these experiments at a room temperature and with really large samples. So for example, we can study the scattering medium that made of a lot of small particles, okay, how the light propagate in this kind of system. Or we can study in like an optical chaotic cavity, meaning the ray dynamics is chaotic inside this cavity. This is more like a quantum dot for electron. And also in terms of nanowire for electron, we can study a multi-mode fiber with this random mode mixing. So this is basically is an optical analog for those kind of mesoscopic system for electron transport. And one advantage to study this with photon rather than with electron is that because we have a lot of advanced optical techniques which allow us to really study them in a way which we cannot do with electron. I will show you some example later. But today's talk, I'm going to focus mostly on scattering medium, which there's many examples in our daily life, like a cloud, fog, sandstone, or biological tissue. They all look opaque because light is strongly scattered and then reflected back. So it's not because of absorption. And in this case, so the question is, can we enhance the light penetration into this kind of strongly scattering medium so that, for example, we can send lasers through cloud or enhance our visibility for sandstone or fog, or maybe even allow us to do deep tissue imaging. So by sending light deep into a biological tissue that strongly scatter light. So to answer this question, we have to first see what determines the transmission of light through a strong scattering medium. So here I call a diffusive medium, meaning that the sample thickness is much larger than the transport mean free path. So the transport mean free path is defined as the length light will propagate until its direction of propagation is completely randomized by multiple scattering. So if the thickness is much larger than the transport mean free path, so what does that mean? That means that when the light coming in, then after multiple scattering, most of light will be reflected, a small amount will be transmitted. So the average transmission is approximately equal to the ratio of the transport mean free path divided by the sample thickness. And this is much less than 1. So that's why we cannot see through the this kind of strongly scattered medium. So now the question is, how can we enhance wave transmission through this kind of system? Then we have to really see what determines this transmission. This formula actually coming from diffusion equation. That is assume light is going to a random walk and ignore the phase or the of the light field. So therefore it ignores the interference effect. But experimentally, if those scattering particles, they are static, in space, they don't move, and if we're using a coherent light, then the interference of scattered light could become significant, and that actually may allow us to using the interference effect to enhance wave transmission. So that is our goal, to using this interference effect to break the diffusion prediction. So now let's try to see how we can do that. In order to do that, I need to first introduce this so-called transmission matrix. So let's consider a waveguide geometry, a simple case. Then we have a random distribution of particles inside there, and they are static, they don't move in time. Then we're sending light in one waveguide mode. And then after multiple scattering, most light will be reflected, but a small amount will be transmitted. But this transmitted light was no longer just stay in the fundamental mode, it actually stay in all the waveguide modes. So therefore we can decompose the transmitted light by the waveguide modes and get the coefficient for each waveguide modes. And that gives us one column of this field transmission matrix. Then we send in the second order waveguide mode, find out what is the transmission, decompose by the waveguide modes, get the coefficient, we get the second column here. So by this way, we can build the transmission matrix that is n by n, where n is the number of waveguide modes in this system. So this field transmission matrix completely connects the output field with the input field. So any arbitrary input field, you times the transmission matrix give you the output or transmitted field. So next, what do? We try to find the eigenvalue and eigenvector of T dagger T. That gives us the transmission eigenchannel. The eigenvector gives us the input wavefront for this eigenchannel, and the eigenvalue gives us the corresponding transmittance for this eigenvalue. In other words, if we prepare the input wavefront to be equal to the eigenvector, then we couple into one eigenchannel. The output will be give us the transmittance that is equal to the eigenvalue. So this eigenvalue distribution in a diffusive waveguide without absorption, that has been known for many years. That actually satisfies this kind of bimodal distribution, because this transmittance or the transmission eigenvalue can only be between 0 and 1. So you see that most eigenchannels has transmittance close to 0. So we call them closed channels. But we see a small peak here at a tau equal to 1, and that's actually corresponding to 100% transmission. So that means those channels, if we can couple light into it, it will give us 100% transmission, and we call them open channel. And this can happen for any diffusive system at any wavelength. And even though the average transmission can be much less than 1, we always have some open channels allow us to have 100% transmission. This has been predicted, in the mid 80s by theoreticians for mesoscopic transport of electron. But because of these open channels, they are formed by interference of scattered waves. They also exist for light or for other waves. And for what's the advantage to do this with light is for electron. It's very hard to prepare the electron wave function to couple into a single transmission eigenchannel. But we can do this for light. So that's why allow us to really using this kind of open channel to enhance light transmission through opaque medium.
May I interrupt you to ask a question?
Yes, please.
Okay, in your example of the waveguide, you're saying that there is always an eigenmode that can go through the scattering medium and emerge on the other side without getting out of the waveguide. So nothing gets out of the waveguide for that particular eigenmode where tau is equal to 1?
Yes, for tau equal 1, everything will be transmitted. Nothing will going back. Yes.
And you say that for any waveguide, for any scattering medium, there is such a mode?
Yes. And because this distribution is universal. This is a universal probability density function for the transmission eigenvalue. And that has been derived, analytically, as I said, many years ago. So this is exactly, correct. Yeah.
So nothing gets scattered out of the waveguide.
I'm not sure what you mean by out of, because right now for this waveguide, I only assume the light can either going through it or going back. I don't assume that because the boundaries here is close boundary. So nothing will go to the side.
I see. So it's not like a fiber waveguide where it's possible for the light to get out of the fiber.
Exactly.
On the side.
Exactly. But I will give you another example for a very wide slab later on. This is one example. I'm then going to give you another example with a very wide slab, which have open boundaries. Then you can still have this kind of transmission eigenchannel just going through without going to the side.
Okay, thank you.
But this is just one example. I'm going to give you another example later, okay?
Okay.
So I try to show you, this is really remarkable if you think about it. You say no matter how thick this waveguide is, how small the average transmission is, you can always get a 100% transmission, right? So now let's try to see whether we can see that experimentally. So I'll first show you, one experimental result, then I'm going to show you other cases. So I have to say, people study this kind of transmission eigenchannel also with microwave and with acoustic wave. So I'll show you the example which we're doing here with light. So we fabricated this silicon waveguide, and on silica, and then we basically in one region here we etch a random array of air holes. So that's like a scatters, and then we launch light in. The boundary here we're using photonic crystal layer to have a close boundary. So the light, no matter which direction they hit onto it, it will be reflected back, because they have a full, or complete photonic band gap. So now, so what we are going to see here is that because our input light is at 1550 nanometer, this silicon does not going to absorbing, the input light. However, this light, when they scatter inside, mostly they do in plane, but there may be a small amount that can be scattered out of plane. And that actually, it is kind of dissipation. And that dissipation allows us to probe light transport inside the disorder system. So let's consider our experimental setup here. We're using a CW laser, goes through a spatial light modulator to modulate the input wavefront. And then we using a high, NA objective lens to couple light to the edge, through the edge of this wafer into this waveguide. And then the light will propagate through this waveguide and then go into this disordered regime. They go through multiple scattering, propagation, and there's small amount of light to the top we can collect it with another object lens, and then go to the camera to see what's going on. So this is our setup to really see to probe light, transport inside. And then basically our goal is to adjust this wavefront to enhance or, we can also suppress the transmission through this disordered waveguide. So let's first consider if we just don't, adjust wavefront like a plane wave or any arbitrary input wavefront. So in this case, we can monitor the intensity distribution inside this disordered regime. So this white, rectangle tells us the edge of this, this area which has a random array of air holes. So when we see from the top, the light coming from here, when we see the top, we see the intensity will decay as it propagates through the system. If we do cross-section average the intensity here, you see this cross-section average intensity shown as this red line here, they decay almost linearly with the depths. This is a prediction by the diffusion equation. There's a slight deviation because we have a little bit of dissipation, so it's a slight deviation from linear decay. But the transmission is about 4.7%, through the system. Now we try to adjust wavefront to couple into the high transmission eigenchannels. Then we see what happens. So in this case, we can see that if we maximize the transmission, now the distribution of light intensity inside the disordered system is completely changed. It's no longer decaying, but it's actually peaked near the center of this waveguide. And the transmission now goes to 48%. So that's 10 times more. So that means by just adjusting input wavefront, we can not only enhance the total transmission, we can also completely change the, this light intensity distribution inside the system. And this is corresponding to couple to the open channels, because open channels has the spatial profile. It is peaked near the center of the waveguide. And now if we want to couple to the closed channels, then we can suppress the transmission. So now you see, now we can, reduce the transmission to 0.1%. That's about, 47 times smaller. Now for this, in this case, the intensity distribution decay exponentially with the depths. So now you can see that this is actually corresponding to the spatial profile for the closed channel. That's why they have very small transmission. Most light is reflected. So this is a simple experimental, setup to show that indeed for the same structure, by just changing the input wavefront, we can change the transmission about 500 times, and we can also change dramatically the intensity distribution inside. And this actually is done by manipulating the interference of the scattered waves. So in one case, previous case, we make the scattered wave interfere constructively when they're going forward to enhance the transmission. In the other case here, we actually try to, make the interference for the forward scattered wave, they are destructively interfere to suppress the transmission.
May I interrupt you again?
Yes, please.
Okay, you said that you are monitoring the light from above the waveguide. You have put your microscope objective above the waveguide to monitor, to produce these pictures, basically. But then you said that whatever is not transmitted, it's reflected back toward the source. So are you saying that there's just a small amount that's scattered toward your detector, monitor?
Yes, yes. We actually, exactly. So this is not an ideal case, which I showed previously theoretically. So in this case, the light can be, when they're coming in, they can be reflected, they can be transmitted, and the small amount can really, scatter out of plane. And but we try to optimize the size and the size of the air hole and the density to reduce this out of plane scattering, so that it allows us to see what's going on inside, but it's not a very significant loss. Okay. That can be seen from here, because if there's no loss, the intensity distribution inside the diffusive system should be a linear decay. Now, because we have a small amount of loss, you see there's a little bit exponential, but not very significant. This actually coming from the out of plane scattering. So it is indeed, this tells us the loss. There is loss there, but it's very small. So this decay is almost linear as what we know. So this blue line, it is a prediction from diffusion equation. There, yeah. Okay.
So how do you control the lost light into the detector, into your monitor in this case? Is it because you have a high refractive index in the silicon waveguide and you don't expect much to get out?
Because we have this thin silicon layer, and then we have air on the top, we have silica at the bottom. So when you drill this holes there'll be a small amount that can be scattered, top or to the bottom, but usually we can make it fairly small. Yes.
Okay, thanks.
I can also adjust and make it large. I'm going to show you another example. We can try to make it intentionally make somewhere large. So here, so previously I considered it's a homogeneous scattering system. So here is a inhomogeneous scattering system because many scattering system is inhomogeneous, right? So now we try to, in the center regime, we try to make this air hole there is larger and denser. So therefore we can enhance this outer plane scattering because the air hole is larger. So that means we have more loss in the central regime. So now we try to see in this case what happened to this high transmission eigenchannel. So first of all, we just have a random input. We don't do any, optimized wavefront. So now let's try to see what happens, when we see from the top. Again, we see the intensity decay with the depth, but in the central part, it is bright. That's because here we have more outer plane scattering loss. So that's why we see there's a bright part there. Now we try to couple to the high transmission eigenchannel. Now you see the center part becomes dark. That's because this high transmission eigenchannel try to bypass the central region that is lossy so that they can, enhance the transmission. So now you see that the intensity outside, it is larger, and the inside here, it is, lower here. So again, this is done by interference effect. By adjusting input wavefront, we can make the scattered waves, which go through different paths, then reach the central regime. They interfere destructively to minimize the intensity. And then outside this regime, they interfere constructively, so they can make the light to go, bypass this central lossy regime. So this basically shows that we can steer the propagation of light in a highly scattered medium. This is a very strong scattering medium. The transport mean free path is just about, is less than 2 micron. So it's a highly scattered medium. And this length is about 50 micron. We can still steering the light propagation deep inside the system by control the input wavefront. Okay. So that is just one example to show how we can, deliver light deep into the system. Now the next one, I said, this is a simple example for the waveguide. It's more like a textbook example. In reality, we usually don't have this type of waveguide with the closed boundaries, right? So let's consider, experimentally, very often what we have an open slab geometry, meaning that the width is much larger than the thickness of the slab, and we have open boundaries here. Okay, so in this case, the question is, what is the transmission eigenchannel? Can we still have 100% transmission through it without leakage to the side? That's, I think, you asked earlier. So here is transmission eigenchannels. So this basically is a very large, very wide slab. Now you see this high transmission eigenchannel. They are not spread over the entire slab. Otherwise, they're going to have a leakage out. They actually spatially localized at some particular regime. And another one is here, another one is here, another one here. So basically, we find that for a very wide slab, the transmission eigenchannels, they are localized. They are spatially localized in certain regime, and their input and output size, if you think about the width at the input surface, at the output surface, they are equal. So there's no lateral spreading even. So we call this the transverse localization of transmission eigenchannel, and this happens in a diffusive system, because we know light can be localized in strongly, like a strong scattering medium where you have understood localization. But here is even in a diffusive sample, for wide slab, the transmission eigenchannel can be spatially localized, and then they can have 100% transmission. There's no lateral spreading, so they don't leak out to the side. And so this basically shows the difference. So typically for diffusive sample, like a diffusive slab, if we send in incoherent light, and we know when they diffuse in the forward direction, they also diffuse in the lateral direction, so they spread. However, for the transmission eigenchannel, they don't spread. If we adjust the input wavefront to couple into one transmission eigenchannel, they are basically have the same width at output compared to the input. Again, this is an interference effect, constructing interference of scattered waves. And this actually is very appealing because that means that not only we can have 100% transmission, but because the transverse localization, the area is also small, so we can have high intensity because the energy density it is the transmitted power divided by the area. If the area is not spreading, then we can have more enhanced energy density, both inside this diffusive waveguide and the diffusive slab, and also at output. And so there's a lot more details about this, but I think I'll skip that. I'll be happy to answer, answer any question, if you have.
Is it two-dimensional structure or three-dimensional?
Numerical simulation we did for 2D. Experiment we did this for 3D. 3D slab. It's like a paint. We really do for paint. We just have a paint, and then we just put it on a glass substrate. And then we show this transverse localization of transmission eigenchannel.
And this is monochromatic light?
Monochromatic light.
Very narrow band?
Yes, yes. And that's what I'm going to talk about next, the bandwidth of transmission eigenchannel. So indeed, right now we're using a single frequency or a very narrow band. So we're using this interference effect. So now if we, as I said, this open channel exists for any frequency. Right, but for different frequency, you have different input wavefront to enhance the transmission. So therefore, if we fix our input wavefront to this kind of open channel at one frequency, then we start to scan the frequency. Then the transmission will going down because you are no longer, this wavefront is no longer the wavefront for this high transmission channel for different frequency. So therefore, there's a narrow band. And this bandwidth is determined actually by the inversely proportional to the dwell time of light in this diffusive medium. And that actually is determined by diffusion coefficient and the thickness of the sample. So now the question is, can we make this working for broadband light? So what do you mean by broadband light? Okay, so if I have a broadband light has many different frequencies, of course, if I can separate each frequency and then tune their wavefront to be equal to the transmission eigenchannel for that particular frequency, of course, we can still get 100% transmission. But that's very hard to do. So typically, if we have a broadband, we have to adjust the spatial wavefront for all these frequencies to be identical. We can, just shine them onto a spatial light modulator, and all frequencies will be, modulated, simultaneously, then they'll have the same wavefront. So now the question is, with the same wavefront, can we still find a wavefront that can enhance the transmission for all different frequencies simultaneously? And the answer is yes. So this basically shows one example where the input bandwidth is 40 times of the bandwidth of this high transmission eigenchannel. So if we can find a wavefront that, of course, we cannot reach 100% transmission at any frequency, but over a much larger frequency range, we still can have a very significant enhancement. Because if you can see this black dotted line, that is average transmission. So average transmission through the system is much lower compared to this blue curve, this red curve, which show us we can significantly enhance the transmission at many different frequencies simultaneously using a single optimized wavefront. Okay, so that means indeed we can do this for broadband light. but we cannot get into 100% transmission. But we can still enhance transmission about like 10 times. That's no problem. Okay, so this is basically for enhanced transmission. Now let's consider whether we can do this also for reflection. So we consider a simple case. First, we consider we have some, like say, actually absorption. This is coherent control of absorption, not reflection. Sorry. So let's consider we have a waveguide that is closed on 3 sides. And then we have some, small absorption in the system. This is a numerical model first done by Professor Doug Stone and his postdoc Yidong Chong. So they assume just adding some imaginary part to dielectric constant, assuming that is as absorption. So then what they, so in this case, light either be absorbed or they are being reflected. However, they said that the scattering is much stronger than the absorption, so that most light will be reflected before they have a chance of being absorbed. So therefore, in this case, we still see the sample almost like a white because most light is reflected. Now, in this case, of course, we can also build a reflection matrix to connecting the input field with the reflected field. And then we find what is this reflection matrix, what is eigenchannel for this, for this reflection matrix. And then we can see this eigenvalue, which tells us the reflectance for each eigenchannel. You see they spread over a very large range from 0 to 1. Most channel has reflectance, close to 1. That means that they're just going to be reflected. But at any frequency, there's always a channel with reflectance almost 0. That means the light will be absorbed, because light can either be absorbed or reflected in this case. So that means that by adjusting the input wavefront, we can control the scatter, the interference effect to dramatically increase the dwell time of light inside this disorder system, so that the light will be eventually absorbed. So that's why we can really change the dwell time of light inside the strongly disordered system. So rather than quickly reflect it back, they can stay there for a long time. So for this, we actually did experiments just using the Diasynthesis solar cell. So Diasynthesis solar cell is basically has this scattering cathode that made of titanium dioxide, porous medium, and then they coat with dye. It is immersed in the electrolyte, and then sandwiched between 2 transparent electrodes. So the light coming in will be absorbed by dye, generate the electron-hole pair, and then electron going to propagating through this titanium dioxide to one end, to one electrode, and the hole goes to the electrolyte, go to the other electrode. That gives the current. So here, by adjusting the input wavefront, here we cannot, we had to do optimization here. By just optimization, we can either enhance the short circuit current 2 times, or suppress the short circuit current by 3 times. So that means that we can really change the short circuit current or the absorption by changing the input wavefront. Of course, this is again, I'm not saying this can enhance the efficiency of the solar cell, because that's usually using white light. This is still a coherent light. But that's basically tell us we can really deposit the energy into different area inside the system, and that can allow us to probe this photoelectrochemical process in this kind of opaque cell, and that can give us some physical insight that may help eventually to improve the efficiency of those cells. Okay, so I think that's just a very brief thing about coherent control of absorption. So basically, let me try to summarize the first part of my talk. I show that actually we can, achieve coherent control of light propagation and absorption in a strong scattering medium by shaping the incident wavefront of a laser beam. So because this allows us to manipulate the wave interference effect to break the incoherent diffusion limit, and that allow us to achieve very diverse transport behaviors. So this is the first part of my talk. So maybe I'll stop here for a second before I move to the second part to see whether there's any further questions.
So when you did your first example with the waveguide, you talked about the mode that gets transmitted by a certain amount, and you constructed a transmission matrix to find its eigenvalues.
Mm-hmm.
And in the second part, you had a wide and thin slab with some inhomogeneous medium, and then you showed how to maximize transmission through it.
Yeah.
What was the modal structure of the beam? Did you just break it up into plane waves?
What is the mode of what? Sorry?
Modal structure, because in the case of the waveguide, you knew the modes, but here you don't have any waveguide, so your modes are just ordinary plane waves, I suppose.
Yes. So basically, this one just a transmission matrix. You really describe that in, or measure it in any basis. So here we can do the from input the K space to the output the K space, or we can the real space, different position at the input wavefront to the field at the output wavefront. In the near field. So transmission matrix can be measured in many different bases. So here what we are measuring the K space. So we send in the light in a different plane wave, and then we measure the transmitted wave in the far field, also in the K space. But there are also people try to measure in the real space. In other words, they basically focusing light into different spots at the input surface and then measure the transmitted field at the output surface. That's fine too.
So you either use the Huygens wavefronts or the plane waves?
Yes. You can use any other wavefront too, but just as long as they are complete basis, that's fine.
Sure.
They all give you the same transmission eigenchannels.
Of course, yeah. Thanks.
Yeah, sure.
Yeah, I have a question.
Yeah.
So this is a very interesting material. So my question is about transmission matrix. So in that matrix, it describes the statistical properties of the medium, or it describes some precisely the distribution of the particles in the medium.
So basically, this input wavefront, what is input wavefront give you the high transmission will depend on what is the configuration of all these scatters or these scattering particles. But we don't need to know the spatial distribution of scattering particles in order to find the high transmission eigenchannel, because we can just measure the input-output this kind of field in the far field region. For example, I can send in the plane wave and measure in the far field. And then using this, I can find the transmission eigenchannel. But of course, the transmission eigenchannel profile depends on the configuration of the particles. If you have a different configuration, you still have high transmission eigenchannel, but they are basically the wavefront to couple into them will be different.
Okay, thank you.
Okay, all right. So this part a little bit more related to the physics part, maybe. So next part, I'll try to show you one application using disorder system. So here part of it, I would say we try to overcome the disorder, effect, or compensate for the disorder effect to enhance transmission or absorption. But next part, I'm trying to say we are trying to utilize disorder for some device application. So I'm going to show one example for spectrometer. So we know for spectrometer, if we buy a spectrometer, what we care the size, cost, and the resolution, right? So if we want to go to, higher resolution, we usually the spectrometer is large and it's more expensive. With a smaller, spectrometer, they're cheaper, but the resolution is not so good. The reason is because if we open all this spectrometer, we see they all based on the same, principle. In other words, they're all using the grating to diffract light. So let's consider if we want to using the grating to diffract light of different wavelengths into different spatial location, so they can be measured by the detector at a different, spatial location. We see that if we want to have a high resolution, We need to have a grating with large size and fine grooves. We also need a large distance between the grating to the detector, so that if the two wavelengths are very close to each other, their diffraction angle is very close. So you have to really propagate long enough before they can be separated and measured by two different detectors at different spatial locations. So therefore, the resolution scales as 1/L. If the larger the distance, usually the resolution will be better. But of course, this one here, that means that if you have a smaller footprint, of course the resolution will suffer because you cannot make them really large, this kind of distance. But this is because the light propagating in the free space, so that it goes straight, in a straight line. So in order to really reduce footprint but still increase the path length of light, we can using a disordered medium. Because when we're using a disordered medium, when the light coming in, they don't travel in the straight path. Because of multiple scattering, they go through this kind of zigzag passes, and then eventually maybe someone will go through. So therefore, the actual path length is much larger than the actual dimension of the system or the footprint. And of course, light is not just going through it with a single path. They can go through many different paths, and then they can interfere, and then that gives the speckle pattern. And this speckle pattern will be different for different wavelengths because this formed by interference effect, so it's really sensitive to the wavelengths. So therefore, the speckle pattern can be used as a fingerprint to recover the wavelengths of the input light. So in terms of the resolution, if we consider a diffusive medium, the average path length of light inside this medium, it is proportional to L²/LT. So that means compared to the linear dimension L, the path length is enhanced by a factor L divided by LT. And this can be very large, maybe like say 10 times, 100 times. So can really increase the average path length a lot. And more, so therefore that means the resolution spectral resolution will improve. And the resolution now scales as 1/L² because there's L² here. So that means if we increase the footprint L 10 times, here we can enhance resolution 100 times. But here we can only enhance resolution 10 times. But we pay a price. So the price we pay is the transmission scales as LT/L, as I just said. So therefore, the resolution is higher, but the transmission is lower. So that means we cannot we can have high sensitivity, but we have no signal to measure anymore. So the question is, can we still enhance resolution without paying the price of reduced signal strengths? So to do that, actually we can do that. We can do it on chip again. So let's say we have a silicon uninsulated wafer. We make this kind of random array of air holes in this half circle. Okay, that's as a scatters. And then when the light coming in from the base here, after multiple scattering, most light want to come in going back. To avoid light reflecting back, we put this photonic crystal layer at the bottom. And they have a full band gap, so they basically the light when they reflect it, they'll be reflected from this photonic crystal layer and then moving forward. And we're introducing a DFAT waveguide to really guide light into this disordered regime. And this eventually coupled to a ridge waveguide from the edge of the wafer. And then therefore light cannot going back, they have going forward. When they're going forward, reach the other side of this disordered regime. And then again, we make this kind of output waveguide, which is tapered. So they are tapered, eventually the width is at the end is equal to the size of photodetector. So therefore each channel can really measure the intensity will collect light for one photodetector. In between this waveguide, we put a photonic crystal layer again. So if the light does not hit one of the waveguide, they hit in between them, they actually will be reflected back into disordered medium. After multiple scattering, they try again to hit another disordered waveguide. So in this first experiment, we did not actually make the integrated photo detector on on this chip. Instead, we try to make a groove so we can scatter light to the top. Then we can measure that using a camera. So basically, what we're trying to do is that for different wavelengths, they're going to have a different intensity distribution over all this detector array. So therefore, we can use this intensity distribution as a way to, as a fingerprint to recover the input wavelengths. So what determines the resolution? The resolution is determined by, if we have this intensity distribution over this detector array, how much wavelength shift will cause this distribution be different. So this can be described by the spectral correlation function to correlate the intensity distribution at two different wavelengths. So with increasing wavelengths, spacing, this correlation will going down eventually because they are no longer correlated, and this width give us basically this estimation of the spectral resolution, and that's also basically tell us how much we have to change before we can get a different intensity distribution or speckle pattern to really recover different wavelengths. So here in this case we have about 0.6 nanometer.
So what are you measuring here? You're measuring the intensity coming out of different output channels?
Yes.
Not the spectrum, but just the intensity.
Oh, just intensity, of course. If I measure spectrum, then this is not a spectrometer. So spectrometer is that I come in, I don't know what is the wavelength. I just measure the spatial intensity distribution. I can recover the wavelengths. And
from the intensity distribution, you can tell what wavelength you had.
Yeah, because different wavelengths will give you a different speckle pattern at the, or different intensity distribution at the output. So we are using that as a way to recover the input wavelengths. So how we do that? This is basically how we do it. Each wavelength gives you an intensity distribution over all detectors, and they are different. So for each detector, the total intensity, the sum of the intensity from different wavelengths, because different wavelengths don't interfere. This is a time integrated measurement. So different wavelengths don't interfere. So we just add their intensity together. So in this way, so lambda 1, lambda 2 is the intensity for different wavelengths. It's not the wavelengths, just the intensity at each wavelength. And this I is intensity at each detector. So this can be expressed in a vector form like this. We have a vector of the I is the intensity at different detectors. S is the intensity at each wavelength. They are related by this we call the transfer matrix, which is basically has each columns tell us what is the intensity distribution for each wavelength. So now with that, we actually can see that if we calibrate this, if we know, or we can design this this transfer matrix, if we know this, and then for any input spectrum which we don't know, by measuring the intensity distribution, we can recover the spectrum.
Wait a minute. So your light that's coming in has all the wavelengths at the same time, simultaneously, right?
Yes, yes, yes.
And so you're measuring the intensity simultaneously. So all the wavelengths are in the output spectrum also.
Yes.
So
but it's a different linear superposition, because each wavelength has a different intensity distribution. So the total intensity pattern is a sum of the intensity pattern, incoherent sum of this intensity pattern of each wavelength. So that's why they're related by this linear matrix multiplication.
I see. So you calibrate the system for each wavelength separately at first.
Yes.
And then once you have an input pulse, you find out what that superposition is, basically.
Yes, exactly.
Okay.
That gives us the spectrum.
Okay.
So that's we can do this. So as long as we know M, and then we can do it in the matrix inversion, we can find what is a spectrum from match the intensity distribution. So of course, this matrix inversion is ill-defined if I have noise. So we can also do this kind of optimization to minimize the difference between I and M times S. So here shows like a few different spectrum we can recover simultaneously. That is multiple lines or continuous spectrum using this way. So here, as I said, because we're using the multiple scattering to enhance the spectral resolution, and this kind of enhancement is broadband for any wavelength. It will happen. So therefore, we can get a enhanced resolution over a fairly broad wavelength range. So here we show that for just for this, we have the diameter or the radius of this, disorder regime is 25 micron, and we are able to, resolve two lines separated by 0.75 nanometer, just from their intensity distribution outside, simultaneously, because it's not just line width of each one. This thing here. So that's basically tell us that actually we have a fairly good resolution, for this very small footprint. The next question is how many wavelengths we can recover simultaneously. So the bandwidth of this spectrometer, which means single measurement, what is wavelength range we can cover, is equal to the number of the detectors we have, because that will determine the number of independent spectral channels we can measure simultaneously. So this is N, and then times the bandwidth of each channel. That is our spectral correlation width, which I talked about earlier. So this actually give us, the bandwidth, what we can measure. But what the advantage here compared to the conventional spectrometer is that even I can only measure, if I have only 25, say, detectors, I can only measure 25 spectral channels simultaneously. But this 25 spectral channels doesn't have to be next to each other. Because if I know in my signal, I have only some light at some frequency range, and then there's nothing in between, then I have signal in a different wavelength range. I can build my transfer matrix that contains the speckle patterns or intense patterns only for those wavelengths. So therefore, this 25 spectral channels can cover a fairly broad range. They don't have to be next to each other. And then we can use this to really kind of recover the spectrum, to cover spectral channels well separated in frequency. So this actually leads to one advantage of this random spectrometer. So typical grating spectrometer, they are using one-to-one spectral to spatial mapping. Mainly one wavelength is mapped to one spatial location. Different wavelengths mapped to a different spatial location. This is a way to recover the spectrum. In this case, if I have a small number of detectors, and some wavelengths don't, they do not reach the detector array, they will be lost. We cannot recover them. So that's why we need to rotate the grating in order to measure light from different wavelengths, right? But if we want to make it on chip, we cannot rotate our grating anymore. It is etched into the wafer. So now if you consider disordered system here, each wavelength generates like a random distribution of intensity over all detectors. Different wavelengths has a different intensity distribution. As I said, that's how they can use as a fingerprint to recover the spectrum. But in this case, you have a small number of detectors, and then all the light still reach there. So that means if I have some prior information about the spectrum, then I can still recover all these spectral channels using compressive sensing algorithm. So this is actually really compatible with compressive sensing. And another advantage of this random spectrometer is that we do not have free spectral range. So we know for grating spectrometer, if for one wavelength, it differs into one angle, then half of that wavelength, second order diffraction will go to the same direction. So that's why you have a certain range, you can measure, because if your wavelength range is larger than this one, then you cannot distinguish lambda 1 and also lambda 2 because they all differ light into the same direction. So that's a free spectral range. But for random spectrometer, if two wavelengths are well separated, it's very unlikely they can generate exact the same speckle pattern. And this chance is very low because the random medium remove any symmetry, any degeneracy that is possible. So therefore, usually the fingerprint are very different if you have many speckle patterns. So therefore, we can cover a very broad frequency range, without worry about this kind of, finite free spectral range here.
So that's very beautiful. I see what you're doing. It's wonderful. But why do you need those spokes that direct you to the detectors? Why can't you just have a hemispherical shaped scatterer with a mirror at the bottom, bring the light in, and then put an array of detectors on the surface of the hemisphere and detect the pattern? Why do you need those spokes?
You don't need to do this way. Actually, yes. Actually, people also later on do this for integrating sphere. You can just, send the light in, and then you have this rough surface. They just do multiple bounces. Then you see the output speckle pattern.
Right.
Yes, then you just put a camera in there. That's fine. But this is on chip.
But still, you don't need the spokes. You can have one dimension or a two-dimensional array of detectors rather than three-dimensional.
Yes, I do. Yes. Well, yeah. Yes, I think you can. Yes. So this is just the first design. As I said, I'm trying to show this principle. I'm not saying this is the best design or this is something, but I want to say one last thing before, before I end, because, okay. So as I said, I have this, mirror. I supply the reflection. I make the light going forward, but as you said, later light can also scatter to the top, right? So that's a loss. And that loss will limit once a path-length light can stay in here, that eventually will limit the resolution and also the sensitivity. So how can we eliminate the out-of-plane scattering loss? We don't need to do something complete disordered. We can engineering disorder, meaning that we can basically introducing like short range order, long range disorder. This is like we call the photonic amorphous structure. Or we can introducing long range order, short range disorder. There's like a deterministic aperiodic structure. For example, there's a golden angle spiral lattice. So in this way, we can control, because by control the spatial frequency components in the disordered medium, we can control the out-of-plane scattering loss. So in this way, we can minimize the out-of-plane scattering loss. So you can see here it's much less compared to this case here, so that we can have more sensitivity and also more, also high resolution. There's more reflection here because this is a impedance mismatch from this waveguide to the disordered medium, and that can also be optimized, but we didn't do that here either. So let me summarize the second part of my talk. Basically, I showed that we can make an on-chip random spectrometer that has small size and a good spectral resolution, because we can enhance resolution using this multiple scattering in the disordered medium, and that's a non-resonant enhancement, broadband enhancement. Because if we can also using a cavity to enhance the the dwell time to enhance the this kind of spectral resolution, but that only exists for certain frequency. Right here is for any frequency. So, and also we don't have a free spectral range. We can work for extremely wide frequency, of input light, and also is compatible for compressive spectroscopy. So finally, I'd like to acknowledge all the people who have done the work. This is the list of my formal and current postdoc and grad students. And also we work with Professor Doug Stone and his postdoc at Yale, Applied Physics Department, and Professor Charlie Schutmeyer and his student at the Chemistry Department. I have been also working, with Professor Alexei Yamilov and his student at the Missouri University of Science and Technology. Okay, so with that, I'll stop here. Thank you for your attention.
Thank you. That's wonderful.
Thank you.
So if I may ask one last question.
Sure.
The spectrometer, you said you are trying to minimize the scattering outside of the system. Why don't you just put a mirror on the top surface and the bottom surface?
Well, top surface I probably can put it, but the bottom surface is hard because it's a very small, our size is very small. It's like the total size about like say 50 micron, and the substrate is about 300 micron. So even you put a mirror here, when they can go in, they will not going back. You have to really make the bottom really thin your substrate, right? The top you can, but the bottom is hard. So that's why people make this into 3D. You can make an integrating sphere. Right. And then they got into, femtobeta resolution, which is amazing, much higher resolution than what we can get for on-chip.
Okay. Thank you.
Mm-hmm.
So do we have any other questions?
Yeah, I had a question.
Yes.
I'm Ewan McLeod. I'm an assistant professor here. I was going back to the first part of your talk when you're searching for a high transmission channel. What sort of algorithm do you use to do that search? I assume you maybe start with a random pattern or a random mode, for example, and then you do gradient descent or something, or is it a genetic algorithm, or how do you find the transmission channel?
Okay, so we can find transmission, eigenchannel by measuring transmission matrix. Okay, so as I said, by finding the transmission matrix, we can measure just the eigenvectors, because that is a global maximum. Of course, you can also do nonlinear search, but nonlinear search very often will be trapped in the local minimum, at least for those kind of high transmission eigenchannels. But you can still do it pretty good. So the way you can do there's many nonlinear but for the solar cell things, we're really doing nonlinear optimization, because for the solar cell, we really for this coherent control of absorption, there's no way we can measure transmission or in any way. So this one here we do nonlinear optimization. Can you see my screen, or do I need to go?
Yep, I can see it.
Okay. So here we have to really go to the nonlinear, because we cannot measure the transmission matrix. So typically we can do different ways. We can do this kind of because really adjust the phase front. We can do as you said, a genetic algorithm, or we can just one by one optimize each individual the phase of individual SLM pixels to maximize the whole thing. So there's many different ways you can do it. You really just the better way you can do it, you can maybe not trap in the shallow local minimum, but maybe a deeper local minimum. Okay. Yeah.
So for that application, genetic algorithms has worked best for you so far?
I think usually no, genetic algorithm we find out is okay, you really have to adjust so many parameters to adjust. So sometimes it's really confusing. So usually we're using the this kind of we call a sequential optimization, which is just adjust individual pixels one by one. Or sometimes we're using this kind of this kind of steepest descent, like what you said. Yeah.
Okay, thank you.
Mm-hmm.
Do we have any other questions? So what is the rest of who?
I have
yes.
a question. So thank you a lot for presentation. At the beginning, you mentioned Anderson localization, so absence of diffusion in scattering. Mm. So do you state then when you optimize this wavefront, find this transmission eigenmode, do you have this effect when you try to, or can you comment on this?
Yes. So far we are all we pretty much stay in the localization. Sorry, we are staying in the diffusive regime, a fairly diffusive regime, meaning that we are still far from the localization threshold. And so in our case, we don't see much effect of the localization. But people does study this kind of transmission eigenchannel in the localization regime. So so basically in the localization region, you still have this high transmission channels, but they cannot give you 100% transmission anymore. But you still can have a great enhancement of transmission for localized samples if you are using this transmission eigenchannel. The reason we try to stay in the diffusive regime is because everything is universal here. As I said, this kind of distribution is no longer true for the localized samples anymore. So this is a pure diffusive, system.
Okay, I see. Thank you.
Sure.
Masood.
Suppose you were going to design your wavefront in your first part of your talk, when you had a waveguide and a scattering medium. Suppose you were going to design your input wavefront experimentally, rather than finding the transmission matrix and eigenvalue, eigenvectors. Because you have a special light modulator, you have control over each pixel. So you could start with a random transmission or phase of each pixel, and then you monitor what comes out. And then try to maximize what's coming out by adjusting each pixel. If the change improve the output, you would implement it. If not, you would go back and try some other change. So is that iterative? Is there an iterative way to experimentally determine the optimum wavefront without going through those calculations?
Yes, you can. Actually, as I said, I think people have done that. We also done that, you know, I mean, at the beginning, to really just, you know, you can do iteration optimization to, I mean, to really enhance the transmission. You can really reach the enhancement. You really can enhance the transmission. But as I said, very often this kind of search will be trapped in the local minima. So you cannot find the global maximum mean transmission. You can maybe enhance transmission maybe 3 or 4 times. But you cannot, it's very hard to reach like 10 times enhancement for the total transmission. Because if you see the landscape for this thing here, is a lot of, you know, this is the problem for the solar system. This is really a lot of like up and downs, a lot of, you know, it's like a speckle pattern. So there's many local minimum here. So you can do this indeed, like what you said, and people have done this. We also have done that. But we found the enhancement we can achieve for total transmission is about, you know, 4 times, maybe 3 or 4 times, but getting into 10 times or maybe even more, that's very hard.
Even simulated annealing or things like that cannot help.
Yes, yes. When people try to simulate annealing, many different algorithms to do it. Basically, is you can really get into not trapping the so shallow ones. You can maybe trap in the more you know, deeper local minimum, but get into the global one. Because you see, the question here is that this high transmission channel is very few of them. Most of them is closed channels. You know, that this is a very few to really have this, to really couple into these things here to have 100% transmission. That's very rare. So you really have to control the things. You know, you really have to find it. You can still enhance it, as I said, but you may not get into 100% transmission.
But do you always have a guarantee that such a peak exists?
Yes, yes, yes. Actually, we measure this one. People also measure this. This kind of. So this has been measured. Bimodal distribution has been measured, and also confirmed numerically. So indeed, there is this peak.
No matter what the structure of the random medium.
No matter what structure of the random medium, as long as in the diffuse regime, as long as there's no loss. As long as you do the complete, you know, input and output of this one here is always there. This is universal AOL. This things here is, yeah, I said, derived rigorously and analytically. So this is a really rigorously derived theoretically by those theoreticians. So this is actually a universal thing. As long as you're in the diffusive regime, as I said.
Right.
Do we have any other questions?
I have a question.
Yes.
It's still about the eigenchannels.
Mm-hmm.
When you have the broadband eigenchannels, do they look very different from the eigenchannels you get for a single wavelength, or do they have any relations with the other eigenchannels?
No. Because this wavefront for these eigenchannels is very different from the eigenchannel for any frequencies. So this one, you really have to find the one for the broadband. I didn't tell you how I find it. Maybe if I just have time, I'll tell you how you can find this one. I'm not doing a search. So let me just say briefly. So for monochromatic light, your transmission is T dagger T, and this is your input wavefront, right? And then this is a transmitted divided by input. This is your transmission. So how I do broadband? So broadband, you can think about it is T dagger T for each frequency times the input spectrum. This is a broad spectrum. So this is my A. So once I know my A is this, I can find what is the largest eigenvalue of A. The largest eigenvalue of A give me the maximum transmission for this broadband light. Just like the largest eigenvalue, for T dagger T for each frequency give you the maximum transmission eigenvalue for a narrow band, for monochromatic light. So using this, we can find it. But this eigenvalue, this eigenvector for this A is very different from the eigenvector for T dagger T for any particular frequency. Yeah. Okay. Is that clear? Hello?
I think she looks a little frozen.
Okay.
Do we have any other questions? So
Coupled wave,
yes.
coupled wave theory. Have you been able to use coupled wave theory to predict, assuming you know the structure of your scatterer, is there any way to use something similar to coupled wave theory to predict what the outcome is for a given input?
Okay, so I think if I don't know much about coupled wave theory, so let me first, if I understand correctly, those things only consider forward scattering, right? So here, so therefore they are usually works when your system, when the thickness is less than the transform mean-free path, because transform mean-free path is the distance when the light is really can travel in all directions. So afterwards there's a strong backscattering. So in our case, we're in the diffusion regime. Our thickness is much larger than transform mean-free path. So we have both forward, backward, a lot of this back and forth. I don't think coupled, mode theory would work in this case, but I may not just know it well enough.
Well, only in the sense that you can take the refractive index of the scatterer and Fourier transform it, then write Maxwell's equations for all the plane waves that are in the medium coupled to each other via individual Fourier components of the refractive index. Now, it could be forward and backward scattering, but there may be a way to adapt the coupled wave theory to calculate the behavior of such a scatterer.
Yeah, there may be a way. As I said, I'm not really familiar with this coupled wave theory, so I don't know whether they can really treat this kind of a highly multiple scattering system, we are having here. But maybe there's a way to, as you said, adapt it to here. Yes.
The basic idea is just Fourier transform the refractive index and then write the Maxwell's equations for plane waves that are coupled to each other via the Fourier components of the refractive index.
Yeah, but I think that ways I think you mostly consider single scattering, because they are just because if you have a multiple scatterings there, and then this would keep like a couple many times.
Well, that's the same as coupled wave theory as holograms. They couple back and forth, but that's fine.
Oh, I see. Okay.
Right.
Okay.
Again, you have eigenvalues, eigenvectors. The coupled wave theory of holographic gratings is similar in many ways. It's just that your structure is periodic. And so you have discrete set of Fourier coefficients for the refractive index. Here, you don't have periodicity, although you could impose it if you wanted to. But you have a random distribution of refractive indices, so there's a continuum of frequencies, the spatial frequencies in the refractive index. But in principle, it should be possible to treat the medium in a similar way by allowing different plane waves, each plane wave to couple to all the other plane waves via the Fourier components of the refractive index.
I see. Yes, yes. So yes, I think that's probably possible. Yes, we are using this so-called recursive Green's function method. Try to calculate this kind of transmission matrix from the refractive index distribution. That's actually also, again, anyway, this is coming from Mesoscopic Physics. So you can build this kind of Green's matrix and then keep using it to really eventually build the transmission matrix. But that's a different methodology. Yeah.
Okay, thank you.
Sure.
Do we have other questions? I see Michael, you've turned on your video. Is that to ask a question? Yes.
It could be, sure. Hi, Professor Hui. I was wondering, you mentioned for, at least on this slide you're showing, they use the largest eigenvalue of this, something like a mixture of the number operator, sort of. Would there be any value in using the other modes as well? Is there any use for those other modes?
Other mode, you mean like not the highest transmission channel, but maybe some other transmission eigenchannel?
Yes.
Yes. So yes. So basically, really, if you don't worry about too much of the transmission, we very often also care about the light-matter interaction inside a disordered medium, right? So so inside a disordered medium, if we want to control, optical process, nonlinear process, whatever. So we want to control the energy, density distribution inside. And that you can do by, using, other channels. You can use different channels because they have different spatial profile to really say, for example, where this most light interaction happens. Yeah, so yes, you can use other channels. You do not necessarily only using the high transmission channels, indeed.
Okay. Would you potentially use multiple of these channels in the same system, maybe for different purposes? Is that kind of what you're getting at? Okay.
Yes, basically right now, actually, I don't have time to talk about this one. We try to do energy deposition. If you want to deposit energy to certain depths in there, usually we're using a coherent superposition of different transmission eigenchannels to do that.
Cool. Thanks.
Okay. Do we have any other questions? So if not, I want to switch to the meet and greet portion, which is slightly different than the Q&A. So it's not a technical Q&A, but it's mainly an opportunity for students to introduce themselves and maybe ask you some questions that are not necessarily technical, but maybe some advice or whatever. So do we have any students that want to introduce themselves and ask any questions? If not, I have some icebreaker questions. Sometimes they're very shy. So my first question I like to ask is, what is the next big thing you would like to see somebody else work on?
Oh, okay, say it again. What's that?
What is the next big problem that you would like to see someone else work on?
Oh, yes. Okay, I see. I think that there's, I think for this thing here, we study a lot of physics about all the things in here. I think there's still a distance to the practical applications. So I think really to bring those things here from this more physicsy part to more, application oriented, really use that in the real system here. There's still a lot of things that has to be, addressed. For example, when we say we can enhance transmission, I can tell you in principle, I can have 100% transmission, but I have to measure transmission matrix, right? So that's, I have to have a detector on the other side, which is we usually don't have. So now in the practical situation, how you can couple into those high transmission eigenchannels? How can you use this in some, realistic systems? You have only limited control. And I think there's a lot of things which we have incomplete control, So I think there's a lot of things which we don't know yet how to apply this to practical, cases. And I think that there's that's what I hope people will really can do this, because eventually, if you really want to use this for non-invasive, say either non-invasive imaging, or people want to think about do this photodynamic therapy to deposit energy into the system or whatever, we really have to find a way how to find the optimal wavefront. Right, without really this kind of invasive measurement, and also these scatters are moving around. They're moving. With time, you have to find the things very quickly. So I think those are really very important big things to really eventually, I think, to have a great impact for this type of work. I think that's very important to do. Yeah.
Okay. My second question is, what is the best piece of advice you have for students?
Oh, what's the best advice I have for students? So I feel that I have crazy ideas. Do things that people usually do not do. So I guess that's just think out of the box, and just try things which you find the most interesting or most intriguing.
Okay, so do we have any students that want to say hi to Professor Chow and ask any questions or advice? Okay.
Well, I just want to say hi to Wei. How are you?
Hey, how are you, Stanley? This is my old classmate at Stanford. So we have been working in the same lab for 4 years, right, Stanley?
We also share the same office.
Exactly. We share the same office, same lab for 4 years. So yeah, nice to hear from you.
Yeah, good to see you. It's a very nice talk. Just to give you an idea, you can also apply the random spectrometer idea to a random polarimeter. So you can measure the Stokes parameter to measure,
Yes, people have already done that. Sorry, Stanley. I know you have.
Okay.
So actually, people using this random, but that's a very good point. People have using this disorder system not only just measure spectrum. Actually, there has been also used to measure polarization state, because that's all. You see, what is the disorder system? It's really they entangle the degree of freedom in many different domains together. You know, like a space to time, spectrum to space, polarization to space. So because of all this entanglement, you can always probe the information in one domain from the measurement in a different domain. So indeed, people can do that already.
I see. Good.
Good idea. Just a little, just too late.
I'm sure a lot of people have worked on it, and all the easy stuff has been done. So.
Masood, yeah.
Did you collaborate with Joe Goodman in any way when you did work on the speckle effect, or was Joe Goodman retired by the time you were at Stanford?
Yeah, no. I think I was a grad student at Stanford, and I think I took class of Professor Goodman, and but at that time I was doing something very different. I was doing like Ms. Stanley said, we're doing cavity QED with semiconductor microcavities. So yeah, so I have not have a chance of working with Professor Goodman there. Yeah.
So he just published his book on the speckle effect.
Oh yeah, we read his paper and his book. A lot of things. It's really, I should say, the Bible, and we learned a lot from that. But I didn't, unfortunately, I didn't have a chance of working with him, because at Stanford I was working on something different, and this was all happens later after I left Stanford. But as I said, his book, his papers, we cite a lot, and really our inspiration. Yeah.
Right. One last question, reciprocity. Have you considered reciprocity in any way in this work? Because in linear systems, if you put the source on one side of the scatterer and the detectors on the other side, and then if you switch them, you get the same thing in backward direction. So if you put the desired output from the detection end of the system, would it propagate backward to give you the desired input?
Yes, I think people, okay, we have not done that, but the people does actually try that. You can send in backwards, what is the desired things through the systems. Yes, I mean, and also people actually using this to do focusing. So how you can focus light through, I didn't have time to talk about that. How you can focus light through a disorder system. Actually, like Professor Chan Wei Yan and other people does, is that they have a source there. They put a guide star. And then they can emit light or whatever, sending whatever. Then you measure it, you phase conjugate it, you send it back. Then you're going to focus there. Yes.
Okay.
But this is hard to do for this enhancement for a large area, because for a large area you don't know what is the pattern you have to send, because we know this is a speckle pattern, but you don't know what is a speckle pattern. So this kind of time reversal things is easy to use for point excitation, but for a large extended area, that is hard to do.
So any students want to be brave enough to say hi? They're too shy.
I can understand. I also, when I was a graduate, I also do not say anything during this kind of colloquium. I fully understand.
Professor, are you still teaching the optics course, the applications of optics course for physics and applied physics students?
Yes. You're from Yale? You're from Yale?
Yeah, I was graduated in 2015. Took your course.
Oh, okay, I see. Wow. So you're in a good place. This is really the strongest place in optics. So, yeah.
Yeah, that was your course is the reason I wanted to study optics. So
great.
The reason I'm here. So I appreciate that a lot.
Okay, well, I'm glad to hear that. Okay.
Just wait, have you gone back to Stanford and talked to anybody or lately or?
Not lately. I have not been, I've been locked down since mid-March, so I have not talked with anybody after, when was my last time to Stanford? I went to the Sigma summer school at Stanford. That was a while ago. Yeah, I haven't been back for a while now. How about you? Have you been back?
No, I think, well, Professor Yamamoto, our advisor, invited us last year, and during the summer, he probably invited you too, right?
Yes.
I was on vacation.
Okay. Yeah, yeah. I was also at a conference. I think I also could not make it, so
Yeah.
I didn't go. Yeah.
That's too bad.
Yeah. Yeah. But I met him at the PQE. I think I met him at the PQE.
Okay.
So,
Good.
any other questions from students?
If not, we should thank Professor Chow again for her great talk and taking the time to speak with us. And we really appreciate you being here. And it's
my pleasure.
Fantastic talk.
I have more time to learn your research and also visit some labs, but unfortunately I cannot travel. I mean, no can travel. Hopefully in the future I'll have a chance to learn more about your research.
Oh yes, that would be fantastic. Yes, absolutely. So,
yeah.
So thank you. Thank you.
Okay. All right. Okay. So.
Thank you very much.
Oh, thank you. Okay. Bye bye.
Yeah, thank you. Good seeing you.
Okay. Nice seeing you. Bye.